Hello everyone. Today I will discuss about monotonic sequences. Monotonic sequence. A sequence Sn is said to be monotonic increasing if Sn plus 1 is greater than or equal to Sn for all n, and monotonic decreasing if Sn plus 1 is less than or equal to Sn for all n. A sequence is said to be monotonic if it is either monotonic increasing or monotonic decreasing. A sequence is strictly increasing if Sn plus 1 is greater than Sn for all n, and strictly decreasing if Sn plus 1 less than Sn for all n. Example: the sequence Sn is equal to n is monotonically increasing. Here for n is equal to 1, S1 is equal to 1, and for n is equal to 2, S2 is equal to 2, S3 is equal to 3, etc. The sequence Sn is equal to 1 by n is monotonically decreasing sequence. For n is equal to 1, S1 is equal to 1, S2 is equal to half, S3 is equal to 1/3, S4 is equal to 1/4, and it is monotonically decreasing sequence. Theorem: every monotonically increasing sequence which is bounded above converges to its least upper bound. Proof: suppose that Sn is a bounded monotonically increasing sequence. Let L be the least upper bound of the sequence, that is the least upper bound of the range of the sequence. We shall show that limit n tends to infinity, Sn is equal to L. To prove this, let epsilon be positive given. Let epsilon positive be given. Since L is least upper bound of the sequence, there exists positive integer m such that Sm is greater than L minus epsilon. Also, Sn is monotonically increasing. So, Sn is greater than or equal to Sm for all n is greater than or equal to m. Therefore, from equation 1 and 2, this is equation 1 and this is equation 2. So, from equation 1 and 2, we have Sn is greater than or equal to L minus epsilon, because Sm is greater than L minus epsilon. So, Sn is greater than or equal to L minus epsilon for all n greater than or equal to m. Again, L is the least upper bound of Sn. Therefore, Sn is less than or equal to L, which is less than L plus epsilon for all n belongs to n, which implies that Sn is less than L plus epsilon for all n belongs to n. From 3 and 4, this is equation number 3 and this is equation 4. So, from 3 and 4, we have L minus epsilon less than Sn less than L plus epsilon for all n is greater than or equal to m. This implies that modulus Sn minus L is less than epsilon for all n is greater than or equal to m. Thus, we see that for each epsilon positive, there corresponds a positive integer m such that modulus Sn minus L less than epsilon for all n is greater than or equal to m. Therefore, by definition of convergent sequence, we have limit n tends to infinity Sn is equal to L. Therefore, the sequence Sn converges to the limit L. 2. Theorem 1 Part 2. Every monotonically decreasing sequence which is bounded below converges to its greatest lower bound. Suppose that Sn is a bounded monotonically decreasing sequence. Let L dash be the greatest lower bound of the sequence, that is, the greatest lower bound of the range of the sequence. We shall show that limit n tends to infinity Sn is equal to L dash. Let epsilon positive be given. Since L dash is greatest lower bound of the sequence, there exists a positive integer m such that Sm less than L dash plus epsilon. This is question number 5. Also, Sn is monotonically decreasing. So, Sn less than or equal to Sm for all n is greater than or equal to m. This is question 6. Therefore, from 5 and 6, we have Sn is less than L dash plus epsilon, because Sn is less than or equal to Sm and Sm is less than L dash plus epsilon. Therefore, Sn is less than L dash plus epsilon for all n is greater than or equal to m. Again, L dash is the least upper bound of Sn. Therefore, Sn is greater than or equal to L dash, and which is greater than L dash minus epsilon. For all n belongs to n, implies that Sn is greater than L dash minus epsilon for all n belongs to n. Therefore, from 7 and 8 we have L dash minus epsilon is less than Sn less than L plus epsilon for all n is greater than or equal to m, which implies that modulus Sn minus L dash is less than epsilon for all n is greater than or equal to m. Thus, we see that to each epsilon positive, there corresponds a positive integer m such that modulus Sn minus L dash is less than epsilon for all n is greater than or equal to m. Therefore, by definition of convergent sequence, we have limit n tends to infinity Sn is equal to L dash. Therefore, the sequence Sn converges to the limit L dash. Theorem 2. Monotone convergence theorem. A necessary and sufficient condition for a monotonic sequence to be convergent is that it is bounded. The condition is necessary. Let Sn be a monotonic and convergent sequence. We have to show that Sn is bounded. Let Sn converges to L. Let epsilon is equal to 1. Then there exists m belongs to n such that modulus Sn minus L less than less than epsilon is equal to 1 for all n is greater than or equal to m. Implies that L minus 1 is less than Sn less than L plus 1 for all n is greater than or equal to m. Let k is equal to minimum of S1, S2, Sm minus 1, L minus 1 and capital K is equal to maximum of S1, S2, Sm minus 1, L plus 1. Therefore, from 1, 2 and 3 we have K is less than or equal to Sn less than or equal to K for all n belongs to n. Therefore, Sn is bounded. Condition is sufficient. Let Sn be a monotonic and bounded sequence. We have to show that it is convergent sequence. Since Sn is bounded, so it is bounded above as well as bounded below. Also, Sn is monotonic sequence, implies that it is either monotonically increasing or monotonically decreasing sequence. When Sn is monotonically increasing sequence which is bounded above, then proceeding as in part 1 of the theorem 1, we see that Sn is convergent. When Sn is monotonically decreasing sequence which is bounded below, then proceeding as in part 2 of the theorem 1, we see that Sn is convergent. This is sequence Sn. Convergent. Theorem 3 part 1. Every monotonically increasing sequence which is not bounded above diverges to plus infinity. Proof. Suppose that Sn is a monotonically increasing sequence which is not bounded above. Let G be any positive number, however is large. Then there exists some positive integer m such that Sm is greater than G. Now Sn is a monotonically increasing sequence. So Sn is greater than or equal to Sm for all n is greater than or equal to m. From equation 1 and 2, from expression 1 and 2, we have Sn is greater than G because Sn is greater than or equal to Sm and Sm is greater than G. Therefore, Sn is greater than G for all n is greater than or equal to m. So, limit n tends to infinity, Sn is equal to infinity. Therefore, Sn diverges to infinity. Part 2. Every monotonically decreasing sequence which is not bounded below diverges to minus infinity. Similarly, we can prove this. Suppose that Sn is a monotonically decreasing sequence which is not bounded below. Let G be any positive number, however large. Then there exists some positive integer m such that Sm is less than minus G. Now Sn is a monotonically decreasing sequence. So Sn is less than or equal to Sm for all n is greater than or equal to m. Now from 3 and 4 we have Sn is less than minus g for all n is greater than or equal to m. Therefore, limit n tends to infinite Sn is equal to minus infinity. Therefore, Sn diverges to minus infinity. Now, example 1. Prove that the sequence Sn is equal to twice n by 7, twice n minus 7 by thrice n plus 2 is monotonically increasing, is bounded and tends to the limit 2 by 3. Solution. First part. Let Sn is equal to twice n minus 7 by thrice n plus 2. This is equation A. From equation A, we have Sn plus 1 minus Sn is equal to 2 into n plus 1 minus 7. Because Sn is equal to this, so we substitute n plus 1 for n. We have Sn plus 1 is equal to twice n plus 1 minus 7 by thrice n plus 1 plus 2. Therefore, Sn plus 1 minus Sn is equal to 2 times n plus 1 minus 7 by 3 times n plus 1 plus 2 minus twice n, this is twice n minus 7 by thrice n plus 2, which gives twice n minus 5 by thrice n plus 5 minus twice n minus 7 by thrice n plus 2. After simplification, we have 25 by thrice n plus 5 into thrice n plus 2 for all n belongs to n. So, this quantity is greater than 0. Therefore, Sn plus 1 is greater than Sn for all n belongs to n. Therefore, Sn is monotonically increasing. 2. We have to show that this sequence is bounded. The given sequence Sn is equal to minus 1 for n is equal to 1, this is 2 minus, this is 2 minus 7, this is minus 5 and this is 3 plus 2, this is 5. So, this becomes minus 1 and similarly this is minus 3 by 8, minus 1 by 11, 1 by 14, 1 by 17, dot dot dot. Thus, we have Sn is greater than or equal to minus 1. Here list value is minus 1. So, Sn is greater than or equal to minus 1 for all n belongs to n. Again, 1 minus Sn is equal to 1 minus twice n minus 7 by thrice n plus 2 is equal to n plus 9 by thrice n plus 2, which is greater than 0 for all n belongs to n. Implies that Sn is less than 1 for all n belongs to n. From B and C, we have minus 1 less than or equal to Sn less than 1 for all n belongs to n. Therefore, by definition of bounded sequence, Sn is bounded. Here minimum value is minus 1, maximum value is 1. Now, third property, this sequence tends to limit 2 by 3. Therefore, since Sn is monotonically increasing and bounded above, so it is convergent. Now, limit n tends to infinity Sn is equal to limit n tends to infinity twice n minus 7 by thrice n plus 2 is equal to limit n tends to infinity 2 minus 7 by n by 3 plus 2 by n, dividing numerator and denominator by n, we have 2 by 3. Thus, Sn converges to 2 by 3. Example 2. Prove that the sequence Sn where Sn is equal to 1 plus 1 by factorial 1 plus 1 by factorial 2 plus 1 by factorial 3 plus 1 by factorial n is convergent, and that 2 less than or equal to limit n tends to infinity Sn less than or equal to 3. Solution. We have Sn plus 1 minus Sn is equal to 1 plus 1 by factorial 1. For n is equal to n plus 1, we have this quantity plus last term will be 1 by plus 1 by n minus n plus 1 factorial. Therefore, Sn plus 1 minus Sn is equal to 1 plus 1 by factorial 1 plus 1 by factorial 2 plus 1 by factorial 3 plus up to 1 by factorial n plus 1 minus Sn is equal to this quantity, which gives 1 by n plus 1 factorial, because this term and this term vanishes, remaining portion is 1 by factorial n plus 1. So this gives 1 by factorial n plus 1, which is greater than 0 for all n belongs to n. Therefore, Sn is monotonically increasing sequence. Again, Sn is equal to 1 plus 1 plus 1 by 1 into 2 plus 1 by factorial 3. This is equal to 1 into 2 into 3 up to 1 by factorial n. This gives 1 into 2 into up to n. This is less than 1 plus 1, and half is, and 1 by 6 is less than 1 by 2 square. 1 by 24 is less than 1 by 2 cube. In this way, this quantity Sn is less than 1 plus 1 plus half plus 1 by 2 square plus 1 by 2 raised to the power n. This is equal to 1 plus 1 minus 1 by 2 raised to the power n by 1 minus n, which is equal to 3 minus 1 by 2 raised to the power n minus 1. In this expression, this is a geometric progression, and its first term is 1 and its common ratio is half. So, Sn is equal to 3 minus 1 by 2 raised to the power n minus 1. Thus, Sn is less than 3 for all n belongs to n. Hence, Sn is monotonically increasing and bounded above, so it converges to its least upper bound, which is less than or equal to 3. Thus, limit n tends to infinity, Sn is less than or equal to 3. Also, Sn is equal to 1 plus 1 plus 1 by factorial 2 plus 1 by factorial 3 plus 1 by factorial n is equal to 2 plus 1 by factorial 2 plus 1 by factorial 3 up to 1 by factorial n, which is greater than or equal to 2. Because Sn is equal to 2 plus some positive quantity, so this is always greater than or equal to 2 for all n belongs to n. Actually, this is greater than 2 for all n belongs to n. So, limit n tends to infinity, Sn is greater than or equal to 2. From 1 and 2, we have 2 less than or equal to limit n tends to infinity Sn, which is less than or equal to 3. This is all about monotonic sequence and its example. Thank you very much for watching. Please don't forget to subscribe my channel. Please like, share and comment. Please press the bell icon to get notifications.